Good evening, everyone. So today we are going to solve a code forces problem, which is from Division 2. It's called Diagonals. So let's check out the problem. So basically, we are given a checkerboard, right? A checkerboard is something just like a chessboard, and it's described that the checkerboard is of size uh, n, which you can basically interpret to it being an n by n side by n side uh, checkerboard. And you're also given k chips. So what does chips means? Chips are basically the elements you basically place on the checkerboard on each and every cell. So here now let's get to know what a diagonal is. So a diagonal is basically the set of cells for which the value I plus j is same. So let's take an example. Yeah. So let's say this is some let's say this is a 3 by 3 checkerboard, and you call it, this is 0 0 0 1 0 2 0 3 0 4 0 sorry, that's my mistake, sorry. uh yeah, 1 0 1 1 1 2 2 0 2 1 2 2. So yeah, now if you see, this is a standalone cell. So we also consider this as a diagonal. But what exactly is a diagonal? So if we carefully inspect these two elements, I mean cells, which it has 0 comma 1, right? Right. And it has 1 comma 0. So what is the sum of these elements? It's 1. Sum of these elements is 1. So basically, uh, you can consider you can consider these two elements as a diagonal, right? And if you consider this, this is 0 plus 2 2, 1 plus 1 2, 2 plus 0 2. So you can consider this as a diagonal. So here also, here the same applies here. 2 plus 1 3, 1 plus 2 1 plus 2 and 2 plus 1 are basically essentially the same 3. So here the sum equals to 1. If for this diagonal the sum equals to 2, for this diagonal the sum equals to 3. Right, and just as the starting cell, we also give this cell uh, the status of a diagonal. So if we have a checkerboard of size n, we can clearly observe 1 2 3 4 5. So 3 4 5, and we can clearly see this see a pattern, which is 2n minus 1. So if there are 6 sides, then we'll have 12 minus 1, which is 11. 11 diagonals, right? So yeah, so basically what we're trying to find is the minimum number of diagonals. What is the minimum possible number of occupied diagonals among all placements of k-chips? So what does it mean? So let's take 1 2 3 4, sorry, 1 2 3 and 4. So this is a 1 2 3 4 5. So this is a 5 by 5 checkerboard. And let's say we have 10 chips, right? So let's imagine each chip like this, a chip. right? This, sorry. Yeah, let's imagine a chip being like this, right? So now we want to place 10 chips in this board so that it occupies the minimum number of diagonals, the minimum possible number of diagonals. So, uh, okay, I'll give you an analogy, right? There is a 10-liter tank, 10 liter. There is a 5-liter tank, two 5-liter tanks. Okay, so if you have 7 liters of water and you want to fill them so that it requires least it requires the minimum number of containers. So I guess it's pretty straightforward that you would dump 7 liters into the 10 liters. It may not fill to the brim, but yeah, your aim has you reached your aim because the containers, the number of containers used is just one. But if you try to fill this 7 liters into the 5 liters, you'll reach the brim, and also the remaining 2 liters you'll fill in here. So now you have filled 2 tanks, and and based on our problem, one tank filling in one tank is efficient more than filling in 2 tanks. So we're gonna apply the same logic here, right? So So we have 10 chips. So which diagonal do you think is the best diagonal that we should fill the first? Obviously, the largest diagonal, right? And clearly, the largest diagonal is this, right? So that's what we're gonna do. Now we're gonna fill here a chip here. One, two, three, four, and five. So as I mentioned in the water filling example, if you had a 10-liter bucket and a 9-liter bucket, after filling the 10-liter bucket, if you had more water remaining, you would probably want to fill in the 9-liter bucket because that is the next biggest or next biggest water container. Just following the same approach, we want to fill the next largest diagonal rather than filling this one or these two or these two, right? So now I'm gonna fill. I've already filled uh, five. So six, seven, seven, 8, 9. Now, if I try to fill these three, it would be right. But what if we had more? If what if we had more, and we had to fill this this three and again these two? That's not nice, right? So we try to fill the see after this diagonal, which has one, two, three, four cells. This is the next largest diagonal, right? One, two, three, four. So we try to fill in this one, which 1, 2, 3, 4, 5, 6, 7, 8, 9. And here is one diagonal. So basically we required 1, 2, and 3. We required 3 diagonals to fill in a 5 by 5 checkerboard, to fill 10 chips in a 5 by 5 checkerboard. We required 3 diagonals. So I guess you're pretty uh, comfortable with what's going on here. So basically what my approach is, fill the largest diagonal, then the next largest diagonal, and then the next largest diagonal, and keep doing that so that you require the minimum number of diagonals to fill. So I hope you understood it, and let's try coding it uh, in Python. Yeah. Now we're trying to code this implementation or approach in Python. Okay, let's just define a function that would basically handle all the logic required for this problem with def. Let's give it a name. Let's give it get min dags, basically, which means get minimum diagonals, right? That's what we want. And we pass in the n and k, which are basically mentioned here, right? The side, which is side of n and k chips required, which is given in the problem. And basically, what we're trying to do is, okay, uh, let's check the first case, right? There are 0 chips given, so you don't need any diagonal to fill it. So that would be our first case, right? So if the number of chips given to us is equal to 0, then we just written 0 because we don't need to fill anything, right? Uh, yeah. So yeah. And now what our approach is? Now we'll keep track of a count variable, which is num number of dags. Okay, which will initialize to 0. Right. So this is basically the number of diagonals which we are going to output as the answer. Right. Now here's the most important part. So basically, if you try to see if we have a 3 by 3 grid, you will this is 3, right? And this is also 3. So basically it's a 3 by 3 checkerboard. You will always have the number of cells in the diagonal of a checkerboard will always be equal to the side of the diagonal. So basically it's a 3 by 3 grid. So in the diagonal, in the largest diagonal, which is you can also call this the principal diagonal, you'll have 3 elements. Same as if you take uh, like probably 1, 2, 3, 4, 1, 2, 3, 4. So basically it's a 5 by 5 grid. And here 1, 2, 3, 4, 5. So the largest diagonal will contain n number of cells. So that's what we're gonna do. So we're basically going to create something that will resemble a diagonal. Let's say diag we can represent as n. So basically we are putting this n number of cells into a list. And now what we're gonna do is, so yeah, what is our basic intuition? We're going to fill principal diagonal first, then the next smallest diagonal, so next largest diagonal, and then the next largest diagonal, and then the next one, and then the next one, and so on, right? So basically, what's happening here? It's clear, right? It's very clear that when you're trying to fill something, it's basically like symmetry. Like this part is symmetric to this part. So basically, the same thing, the same filling, which is going on this side, is happening on the right side too, on this side too, right? Basically, it's like this, right? And this. Yeah, you're feeling like this, and after simultaneous you're feeling like this. So basically we are going to do the same thing twice. So basically let's start now. What we're going to do is, starting from the first diagonal, we'll go till the end, which is, and I told you, right, in the example, if you have 5 by 5 grid, then you'll have a diagonal size 5. That's what we're going to do. So from starting from 1, we're going to 5, which is n, right? So for I in range 1 to n. Now what we're going to do is, we are going to keep, okay, what will add in this list is n minus I. Okay, so what does I mean? You think, so what's I, right? uh So yeah, so what's gonna happen is, yeah, so this initially we have already set diag as n, right? So now we're going to append the next largest one, which is actually n minus 1, right? No, don't get confused. This the upper part has an n minus 1, and the lower part also has an n minus 1. The upper part has an n minus 2, and the lower part also has an n minus 2. So what we should do is we should add the upper n minus 1 and the lower n minus 1. Okay, and the upper n minus 2 and the lower n minus 2, the upper n minus 3, the lower n minus 3, and so on, right? So what we're going to do is, yeah, so basically what we're going to do is dags, so dags dot append, we're going to append the n minus I, and just as I said, we're going to do it two times because there is one diagonal on the top triangle. There's another there is a similar identical diagonal on the bottom corner. So n and minus I, right? So this is the main part. So basically what we have now is it's like this. Let's take a 5 by 5 grid, right? Checkboard. So what we have is 5, 4 comma 4, 3 comma 3, 2 comma 2, 1 comma 1, right? Which basically you can draw like this. I guess if you haven't understood till now, I guess if you will understand by this drawing. This is the 5. Okay, this is the 5. This is this one. Now this is a 4, and this is the another 4, right? Gone. This is a 3, and this is the another 3, gone. This is a 2, and this is another 2, gone. This is a 1, and this is a 1. So basically it's like this. Yeah. So basically, yeah, the one cell, the two cells, the three cells, the fourth cell, and the fifth cell. Again, the fourth cell, the three cell, the two cells, the one cell. It's like 1 to 5, and then 5 to 1. Right. I hope you understand it. So that's what's happening here. So uh these are basically the diagonal sizes, right? Diagonal size, right? So uh what we have here is, let's say in this box we have one, two, one, two. If we have five, right? So one will fill here, will fill here, will fill here, and now basically what we have is, if the diagonal size, which is 5, the diagonal size is less than the number of chips, is less than the number of chips. So basically, if the number of chips are greater than the current diagonal size, we will basically increment the counter, because this diagonal is filled, right? So we need to increment the counter. So I mean, which means by incrementing the counter, I mean the, a diagonal is filled, right? So counter is 1 now. And now after filling 3, we have 2 left. And 1, 2. And this diagonal is filled. So basically 2 diagonals are filled. Right. So that's what we're gonna do. Okay. For diagonal size in the diag list, what we're going to check is, it's just the same thing. The same thing might happen here, right? If there are 0 things given, which is diagonal is greater than, which means you don't have any cells, which means you don't have any chips given. So basically, you don't need to fill in any diagonal. So you return 0. So if k equal to 0, then return 0, right? So next, what we're going to do, sorry, you're not going to, sorry, you're not going to return a 0. You're going to return the count, which, okay, sorry. Have I initialized the count? No. Let's initialize the count to, sorry, give me. That's the count. So basically, if it's 0, then we'll return the count, which is basically 0, right? That's what we're going to do, right? So, yeah. And in the next part, what we're going to do is if if the diagonal size is less than k, what we're going to do is we are going to place all those chips inside the diagonal. Uh, let's just code it up first. Yeah. So what does this code mean? Right. So if the diagonal is bigger than the number of chips, what we're going to do is, so let's say, yeah, in this box, if we have two chips given, the largest diagonal size is 3, and 3 is greater than 2. So the diagonal size is greater than the chips, 2 chips. So what we're going to do is we're going to subtract the chips from the diagonal size, which is 3 minus 2. Why are we doing that? Because we're clearly filling 2 chips, right? So out of the three cells, we are occupying 2 cells, so only one is left. That's what we are doing, one, right? And as I told you, if there is even one cell in the diagonal, we say the diagonal is occupied. So for what do you say? Filling 2 chips in a 3 by 3 grid, we need one diagonal. That's what we're doing. We're basically subtracting the chips which we have placed on the board, and we are and because we have filled the diagonal, or fill or use the diagonal, we'll increment the count, right? So yeah, that's one thing. And or if that is not the case, or if that is not the case, let's say we have 10 chips, right? Right. If we have 10 chips, then no, no, I don't think we can place 10 chips. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. Let's take 5 chips, right? So 1, 2, 3, 4, 5. Right. So what we're gonna do is, if there are yeah, if there are, if you don't have any more chips remaining to place, which is like, see, there might be a condition where like this, right? Yeah, I hope you understand with this one, which is you have placed 1, 2, 3, right? And now you have like, yeah, four chips. You have placed your 3 chips here, and you have placed a single chip here. So what we're gonna do is, what we have is, so just because this diagonal isn't filled fully, that doesn't mean this diagonal is used, right? We have used this diagonal. So it's not just when the diagonal is completely filled. If we also consider if the diagonal is partially filled. So if the diagonal is partially filled, we return the count plus 1, because what we consider as diagonal filling, we normally consider as diagonal filling, is the diagonal getting fully filled, right? But this case does not satisfy a diagonal getting fully filled, because this cell is empty, right? So to not ignore our basic principle, we will return the count and add 1, because this diagonal is also filled. We should not ignore it, right? So we add 1 to the count and return it. So that's what we're doing here. So yeah, that's and after this, we are for the function, finally for the function, we are returning the count. right? So let me take the inputs. These int of input, right? And for in range of t, what we're gonna do is we are going to take n comma k as the inputs. We're going to use a map function which we are mapping the int to the inputs dot split, right? So basically we are taking n comma k n comma k as a string, but we are splitting it and we are mapping integers. So basically we are taking them as two separate integers, right? So yeah, and the result is answer of what get min diagonals, get min diagonals, right? So n comma k, that's where we're going to pass, and we're going to print the results, right? So yeah, I hope this is clear, pretty much clear. So let's run it. Cd code forces, yeah, yeah. So this is uh diagonals Python 3 diagonals 5. So yeah, now let's test these. Let's give input 7, right? 7, 1 comma 0. Oh, sorry, 1 0. You get 0 as the answer, 0. So 2 comma 2, you get 1 as the answer, right? And 2 comma 2 3, 2 3, you get 2 as the answer. And simply if you are going to ignore the other cases and just test for the hard case, 100 and 239, 3. 100 and 239, the answer will be 3. So that will basically be the answer. So let's take it, let's copy the code we just created, and we're going to submit the code. Let's choose a problem. Let's just diagonal and Python, print give our code we just wrote, and we're going to submit it. um, Second bit of time. Yeah, sorry, it took a lot. It took quite a time because probably my internet is slow. So yeah, it's accepted, right? Thank you for watching. Hope hope you'll stick around. Fall for more. Bye.